All right, so we will be performing SMA star on the graph that's given. The heuristic values have been given. These are the heuristic values, and apart from that, the path cost are also given. So to begin with, the start node is S and our goal node is G. We start with S. This over here is the one that is in red is the heuristic value of S. And 0 is the distance of the start node to the current node. So as the current node and start node are the same, that value over here is 0. We need to follow this function, which is f of n is equals to g of n plus h of n. You know, like this is our g of n, this is our h of n. So we add them up. This 12, it comes from, 0 plus 12, 12. All right. Moving on. Now we need to explore S alphabetically. The first child is A and the second child is B. So I'll be exploring A first. Exploring A. The heuristic value of A is 5. The heuristic value has been written in red, and the path, from oops, apologies. The heuristic value is 5, and the path from S to A is 10. So 10 plus 5 gives us 15. Now move, and I forgot to tell you something, that the memory is 4 nodes, so keep that in mind. Now next child being explored is B. The heuristic value is 5 and the path is 8. So 5 plus 8 gives us 13. Now, if both the children have been explored, the next thing that we should do is update the F value of the parent. When you've explored both children, you can update the F value of the parent, and the F value of the parent is updated with the smallest F value among the children. So between A and B, B has the smallest F value because 13 is smaller than 15, right? So 12 gets replaced with 13, all right? So this is how it looks now, all right? Now moving on, we can have a maximum of 4 nodes. So which one do we explore next? We explore the child which has the smallest F value, which is B. Now exploring B, the children of B are D and G. Alphabetically, D comes first. So we are exploring D first. And so if I explore D now, you see that the heuristic value of D is 2. And what about the path, from S to B, from S to B to D, the path is this, which means 8 plus 8, 16, right? So that 16 sits here, 16 plus 2, it adds up to 18. That's how we get this value. Now, since the maximum number of nodes is 4, we cannot add more nodes unless one node is deleted. So among these 3, the one which has the highest F value is D, right? So D should be deleted. This should be deleted. When you're deleting a node, the parent always remembers that node. So in bracket, we need to write 18. We write the 18 of, the F value of D. So as you can see, this is how it looks, right? Forget about this for a while. We'll talk about this later. Just imagine that this doesn't exist for now. So this is the picture. Oops. This is the picture for now. Okay. The box here just represents that D has been deleted. Now, since this is the situation right now, we need to go and explore the other child of B because, we have now these 3 nodes. Forget about this because this has been deleted. So we have explored the D node of, B, the child node of B. And we're going to explore the next child node of B, which is G. So now we're exploring G. The heuristic value of G is 0, that has been written here, and the path from S to G is 8 plus 16, 24, and that has been written here. So 24 plus 0 is 24, and that has been written here, okay? So what next? For a while, you just have to forget about D. This is how the graph looks like right now. Okay, we have 4 nodes. Can we add any extra nodes now? We cannot add any extra node unless one node is deleted, because we said the maximum number of nodes is 4, right? So to be able to add extra node, you need to delete one node among these 4. Now, which one do you delete now? The one which has the highest F value, which happens to be G. So we will be deleting G now. All right. Now to delete G, remember that before we delete G, remember I said that if both the children are visited already, you can update the parent with the F value, which is, like the smallest among the 2 children. Now, like you can see here, B already remembers a child that it has deleted, which is 18, right? And G is 24. The F value of the child that has been deleted is 18, and the F value of the other child is 24. So among 18 and 24, the smallest value is 18. So V gets updated with 18, all right? And like I said, you need to delete G because you have to add other nodes. And you might be wondering why we do not consider this to be the optimal path, because we have, already reached G. So why don't we consider S, B, G the optimal path? G has already been, the goal node has already been reached. The reason why we are not considering this is because we said at the very beginning of the question that the memory should have 4 nodes, and that is not satisfying the condition. The memory here, it has 3 nodes only, S, B, G, right? And that is not the correct path that we're looking for. We're looking for an optimal path which has 4 nodes. So we move on. You can see that B has been updated with 18, all right? And B remembers 18 because that has been deleted. Now we need to delete the node G, like I said. So the node G has been deleted here, right? And how do we know that it has been deleted? Because it's been, marked with this rectangle over here. Okay, now let's go on adding, for a while, I'd suggest you to forget that something like this exists. Just, forget about this. Okay, this is how it looks for now. Right, now, G is deleted, okay? This is the deleted node. This has been deleted. And because it has been deleted, okay, just a sec. It's just checking something. All right. This should bear a 24. Okay. Now let's move on and check the next node that we can explore. The next node that can be explored is 15, because as you can see, among A and B, the node which has the smallest F value is node A. So the smallest child, the child having the smallest F value can always be explored. So we explore the children of A, which is C and G. Since C comes first alphabetically, we will go on and explore C. So that's what it was here, right? C has been explored. The heuristic value of C is 5, and the path from, S to A to C is 10 plus 2, 12. The 12 has been written here. 12 plus 5 is 17. Okay, so this is how it looks now. Well, forget about this delete thingy over here, the square, the dotted line. Just forget about this for a while. Let's just consider that this is not here. It's easier for me to make you understand in that way. Now let's explore the next child, because we have 1, 2, 3, 4 nodes, and let's forget about this also for now. So the next node that I can explore is the next child of A, right, which is G. But to be able to do so, I need to delete one, right, among these. I need to be able to delete one among these three in order to, go and access another node, because my maximum is 4, and this network already has 4 nodes. So I need to delete one to be able to add more and explore more. So the one which has the highest F value, that gets deleted, and that is B. So this should be deleted. Okay, and that is why this had a dotted line around it, right? Okay. And which one do we explore next? The next child of A in alphabetic order, which is G. So yeah, that has been explored too. So you know how this came now. Moving on. See, since both the children of A has been explored, C and G, now A can be updated with the smallest value, F value of the among the children. So between C and G, the smallest F value is that of C, which is 17. So the F value of the parent, which means the F value of A, gets replaced with 17. Okay, and that's what happened here, like you can see. That's it. Now, moving on. Do you see how B has been deleted also, right? The only child left for S right now is A. Oh, and by the way, when we were deleting B, it was important that we write 18 here, because the parent always remembers the deleted child node, okay? And now since the only child left for S is 17, which comes from A, so we update this 15 with 17, and that's where you get this from. But it still remembers 18, the one which has been deleted, okay? Now this is how it looks. All right. So we have 4 nodes in this setup. To be able to explore more nodes, we need to explore more nodes, because this is not the desired path. This doesn't have 4 nodes, it has 3. So although you might think that, I have reached the goal node, this is the end, but it is not. All right, so among these 3, which one has the highest F value? G, right? So this needs to be deleted now. Okay, so if I delete this, I have to make sure that I remember these. All right, so that's why I wrote 20 in brackets close to G's parent, right? And I have this dotted line over G to indicate that this is being deleted. And now I can go on and explore the children of C. So C has children E and G, but since E comes first alphabetically, I am exploring E. And now that I'm done exploring E, I will move on to explore the next node. But before I do that, I have to delete something, right? Otherwise, that's not possible. Oh, wait. Here's what. 4 nodes have already been explored, right? But we have not reached the goal node G. Now what becomes then? This is going to the F value in a case as such, where you have covered the maximum number of nodes, the limit, but you haven't reached your goal. The F value of that particular letter, it gets replaced with an infinite value. All right, and you move on exploring the rest. Now, since E has a very, very large F value, you would have to delete that, and that's what we're doing here. We're deleting E, okay? But make sure you're writing infinite on top of C, because you want to store the F value of the child that is being deleted, right? And yeah, so moving on, let's explore the next node of C, which the next child of C, which is G. So I'm exploring G. the heuristic of G is 0, and the path from, you know, S to A and A to C and C to G, it adds up to 10 plus 2 plus 9 is 21. So 21 has been written here. 0 plus 21 is 21. Now, it might, by the way, since I have, you know, updated, since I have explored both the children of C, I can update C with the F value, which is the smallest F value among its children. So among infinite and 21, 21 is the smallest, right? So I need to update that with 21, and I just did. So here's the thing. The rest of them should get updated as well. I mean, A should get updated also, because we're only left with one child of C of A here, which is C, and S should also get updated. So let's do that. See, among the remembered value 20 and the F value of the child 21, which is smaller, 20 is smaller, right? So you have to replace 17 with 20. All right. And among the F value of the child of S, which is, you know, the F value of A, 20, and the one that the node that has been deleted, the child node that has been deleted, it's F value 18. Which one is smaller among 18 and 20? 18, right? So 17 is replaced with 18. So now the problem is, you might think that this is the optimal solution, but it is not, because I'll write it down for you if that helps. The F value of the root node, the remembered F value of the child of the root node, which has been deleted, is smaller than the F value of the goal node. I want you to be very careful here. Pay attention. 18 is smaller than 21. Now that is the problem. Since 18 is smaller than 21, it might be that the other path, you know, the one that we deleted, B, it could be better than this path. This probably is not the optimal solution. So we have to go back and deal with B now, okay? All right. So one by one, we delete G. And then if I delete G, I will be able to, you know, bring B down, right? If I delete G. And if I can bring B down, in order to expand B further, I have to delete another node, which is C, right? We don't really have to compare anything here, because the only node left here is C. So yeah, there are no other options. All right. And now we explore the next node of D. The next child of, Now we explore the next child of B. We have already explored one child of B, which is D. Now we can explore the other child, which is G, right? So to be able to do so, we have to delete another node, which is A, right? So we delete A, and then we bring down G here, okay? So that's what we did. We deleted A, which has been deleted. And by the way, I don't know if you noticed, but each time I am deleting, do you see how I'm writing 21 here? Because I deleted the child of C. That's why I wrote 21 here. And when I'm deleting A, for example, I'm writing 20 here because I want to remember the child of S that is being deleted. All right? Very important. Now, since both D and G, the both children of B have been explored, now I can update the value of B, the F value of B, with the smallest F value of the children, which is 18. Among 18 and 24, 18 is the smallest, right? So I update it with 18. And okay, this is not my optimal path. So I need to keep exploring, okay? The next thing that you need to do is among these three, because we need to keep exploring. Among these three, which one is the smallest? Which one is the largest? Which one has the largest F value? The largest F value is that of G. So we omit this in order to further explore the children of D. Okay, so the children of D are H and G. So H comes first alphabetically. So of course we should explore H first. Oh, so G comes alphabetically first, so we should explore G first. I'm sorry, I just got a little caught up. So since G comes first alphabetically, I will be exploring G, okay? And the heuristic value of G is 0. And from the start node to G, the path distance is 19. So we get 19 here, all right? And remember, I have already deleted this, so forget about that. But make sure you're writing 24 here because you need to remember the child node that you're deleting always. So this is how it looks like, but we also now need to explore the next node of the next child of D. Although you have reached the goal, you might think this is the end, but this is not the end, because in order for you to update the values, like this value and this value and this value, to be able to update that, you need to go and explore all the child nodes. So the next child node of D is H, all right? But to be able to do so, you need to delete one among D, G, and H, right? So among D, G, and H, the highest F value is that of G. So you delete G and you write H here. So since you're deleting G, make sure you're writing 19 here because you want to remember the child that you just deleted. And since you have done that, this is how it looks right now, but H is not my ultimate goal. So remember what happens when I have already covered the maximum number of nodes, but that is not my ultimate goal. So I replace it with a infinite value, okay? Now I need to keep exploring, remember. So I will delete H, all right? Because there's nothing I can compare it with. That's the only node left. So I am deleting H and I am going to, but wait, before I delete H, make sure I'm writing 19. I have to make sure I'm writing 19 because the child that I'm deleting, I should write it, I should remember it, the parent should remember it. And that's what I did here. And then once, another thing is that you need to update 18 with 19 also because the only child left for B is D, remember? And then eventually you need to update this also with 19 because the only child left for S is B and the value of B is 19, right? And finally, once H has been deleted, you can explore the next node, the next child, which is G. So I wrote G here, right? And I wrote down the heuristic value and the path distance from the start node. So 19 plus 0 is 19, and this is your final answer. This is pretty big, but it's very logical. And yeah, that's it. Goodbye.